This is Unit 8, Video 7. In this video, we'll talk about two more concentration types. And the first one we've discussed before in quite a bit of length is molarity. As a reminder, molarity is moles of solute per liters of solution. Now, a few details about this. This is the most common way of expressing concentration in chemistry. If you go on to chemistry, you'll see molarity used essentially everywhere. There is one drawback with molarity, and that is because molarity is what we call temperature dependent, which becomes a problem sometimes. What we mean by temperature dependent is you have liters of solution, which is volume. Now, when you have volume and you heat up a solution, so here is a solution, say at 22 degrees Celsius, and you're going to heat it up, and now it's going to be 100 degrees Celsius. We'll say we're heating it up to the boiling point. It doesn't have to be water, it could be, but it turns out that the solution will actually expand slightly. Now, we're going to essentially say that we're going to cap this so that way we don't allow any vapor to escape, but still the solution will expand, the volume will change, ever so slightly, but it will change. And if you have a substance that's not in water, maybe another solvent, that could actually have a much bigger effect. So because your bottom here, your denominator will be changing, that's not a good thing in some applications. So that's why we call it a temperature dependent solution concentration, because it's just based on volume, which volume always changes as you heat up a substance. So we've decided to come up with another way of expressing something almost like molarity that is temperature independent, and this concentration is called molality. Notice it sounds very similar to molarity, except now it's an L, molality. We actually use a small m to express it, big M for molarity, small m, and actually a cursive M. So we've decided to use a cursive M for this application, and here's the definition. Molality equals moles of solute, so notice the top is the same as molarity. The bottom is different, so we have kilograms, and we have solvent. So two things are different about this. Number one, it's not liters, it's kilograms. Now that's a good thing because kilograms won't change if you heat up the solution. It expands, but the kilogram stays the same. And it's not solution, it's actually solvent. We defined it based on solvent. That creates a small difference as well, and actually a significant difference. Small but significant. So here it says, since both moles and mass don't change with temperature, molality is then temperature independent. Now, we're actually going to do a lot of converting between molarity and molality. Now, because molarity is moles per liter and molality is moles per kilogram, what we've got to convert from liters to kilograms in order to go from molality to molarity. And what allows us to do that is density. Density is the conversion factor between mass and volume. So we'll actually have to know the density of our solution in order to go from molarity to molality. And we'll be given that, or you can actually measure it. If you have a sample of the solution, you can measure its density as needed. Alright, so let's try an example problem. So we have here a solution of hydrochloric acid that contains 36% HCl by mass. We'll need to calculate the molality of the solution. And then I think we have one that has, yep, we'll do molarity. Okay, excellent. So we'll do two example problems. So this one actually is simply from percent by mass to molality. So again, let's break down 36% HCl by mass means we have 36 grams of HCl and 100 grams total, which means we actually have ourselves 64 grams of water. So that's our breakdown. We have 64 grams of water, which is our solvent, and 36 grams of HCl. Okay, so now for molality, what we need is we need moles of, in this case, HCl, and then we need kilograms of solvent. Our solvent is actually water, so we'll need kilograms of water, of HCl, or H2O. Let's do that. Kilograms of H2O at the bottom. Okay, so let's convert from grams to moles, as we've done before. So to help this out, to convert from grams to moles, you really just divide by the molar mass, don't you? So instead of doing the conversion factor, why don't we just divide by, now HCl is 3545 plus 101, so 3646. So this will give us really close to 1, just a bit lower than 1. So the molar mass here, 36 divided by 3646, 0.987. We'll do 3 sig figs. 9 and 7. This is moles. so we can put that on top. We got 0.987 moles. The kilograms, so going from grams to kilograms, we will multiply by or divide by 1,000. So grams of H2O on the bottom, kilograms up here. So kilo is 1,000. So you divide by 1,000, moving it left 3 times. So we end up with 0.064 kilograms. So if you divide those two numbers, you should get yourself 15.4. So this would be molal. 15.4 molal. Now I guess we have 2 sig figs, so it's really 15. 15 molal. Now with molarity and molality, you can put the letter M behind it, or if you like, you can put moles per kilogram. That's equivalent. So you're free to do moles per kilogram or molal. Make sure that molal is a cursive letter because the non-cursive letter usually designates mass. So molality should be cursive. Okay, let's do the same solution now. We have the exact same solution, except now we want the molarity of it. So you have a 36% solution. Somebody determined that the density is 1.21 grams per mil. And we said that we need density to go from molality to molarity. And that's what we'll have to do here. So again, molarity was defined as moles of solute, in this case we'll do moles of HCl, divided by liters of solution, so liters total, which is different. So in the case of moles of HCl, again we have a 36% HCl solution, so our moles is actually going to be the same, which I believe was something like 0.987 moles. That's correct. 987 moles, and then divided by total liters. Now, what we've got is, in this case, since it's a 36% solution, remember we said it's 36 grams of HCl for 100 grams total, we're actually going to take this 100 grams total and convert it into volume. So we're going to use density to convert it to volume. Remember, density is mass over volume, which means I have the density and I have the mass. If I want to solve for volume, the volume is mass over density. So in my case, I'll do 100 grams of the total solution divided by the density, which is 1.21 grams per mil. And that will give me milliliters. Now, I should say this is grams per milliliters. So coming out of here, we will get milliliters, which we'll have to convert to liters because molarity is defined in liters. So this will actually give us milliliters. So we divide 100 by 1.21, which gets us 82.6 mils. So this is actually, if you divide this by 1,000, remember to go from milliliters to liters, you divide by 1,000, you should get yourself 0.0826 liters. And that's what goes up here, 0.0826 liters. So now we're able to calculate our molarity. 0.987 divided by 0.0826. And we actually get ourselves 11.9 for the molarity. Now again, 2 sig figs, so 12 molar solution of HCl. This is our final answer. Now compare this against the molality that we got, which was up above. The molality was about 15. Somewhere in there. Interesting. Alright, I believe that was about 15, which makes sense. The molality will actually be a little greater than the molarity. That's because the molality was kilograms of just the solvent, so you would divide by a smaller number down here, and so you get a higher molality. A molarity is the total solution, so you get to divide it by a bigger number with molarity. That's when molarity is less. Very famous, by the way, hydrochloric acid. Anytime we order hydrochloric acid, we order it in a stock bottle, and it comes in, on the bottle actually it says 36% of HCl, and it actually says 12 molar. So both of those tags are actually on the bottle itself. The percent by mass, which is an important concentration, way of expressing concentration, and molarity is the first most important way of expressing concentration. Alright, I left you with a little example. example problem to try. So do this practice problem, and we'll try these in class.